Hello, show. Okay. I haven't prepared a PowerPoint because I think this is literally going to be like 10 minutes. Because I know you looked a bit at regular expressions already, Shay, in your session. And then minimal automata is probably like a 5-minute, 10-minute topic. I feel like there's not, because minimal automata is just definitions. We haven't been told any algorithms or anything to do with it, so I think it might be a quite quick session right now. Okay, so I'm going to do the title the other way around. I'm going to be doing minimal automata first, just so I finish off my automata stuff, and then just have a brief look at regular expressions. Alright. Okay, so minimal automata is kind of in the name. What minimal automata is you're trying to represent the language in the shortest amount of states and transitions as possible, which will make its runtime as small as possible. Because there's no point in having a larger automata which is going to take more storage to contain it and also take more time to process it. So what I mean by that is if two languages represent the same thing, so let's say something like this. These two only accept 0 or more A's. Sorry, I didn't make the second one. If we look at these two, they're equivalent. There's no string in this second one, but the first one wouldn't also accept, and vice versa. So they're not minimal. So this first one is not minimal, if that makes sense. It contains more states, so it's more to store it. There's two ways we can check this. So obviously by eye we can see this is not minimal and this is minimal, because there's no way we're going to make this any smaller. But there's two actual conditions. Each of its states is reachable, meaning if we had something like this. Oh, sorry, I didn't do that. That's meant to be A. If each of its states are reachable, so 1's reachable because it's from the start. 2 is reachable. We know we can go from the start, then A. We're never going to be able to get to 3. There is no arrow that leads to 3. Yeah. And then finally, and the other condition is any two states are inequivalent, meaning in this example, if there's a word that X accepts or X rejects, and Y does not also do the same, if Y does do the same, then it's not in its simplest form because you can just combine those two states. So here, if we're starting at 1, so we're not actually starting there, but we're just imagining we're starting there. If we start at 1, A accepts itself, but if we also start at 2, A also accepts itself, so these two are inequivalent, if that makes sense. So why can't reject A? So they're inequivalent, 1 and 2. So that's kind of the technical definition of it, but in the end it's in the name, it's minimal. You want to make it as simple as possible, but that's how you can check if you have a large automaton, if that makes sense. So in this one, we can check, is 7... So first of all, you check they're all reachable. 7 is reachable, 2 is reachable from 7, 3 you can go CB, 18 CA, 95 CC, 18 you can go A or B from the start. So they're all reachable. And then here we can show it's minimal. 2 is inequivalent to the other states. So 2 accepts epsilon, but every other state rejects it. Do you have that? And then it's just that all over again. Yeah, so any automaton that's not minimal, we can be reduced to a smaller automaton by removing the unreachable states, so just deleting 3, or by collapsing. Does it say collapse? Oh no, sorry. Or by choosing to keep one of the states to keep. So if 2 states are the same, we can just collapse them in on each other. So one by one, pick another state. Y, redirect all incoming transition to X and remove the state and all outgoing transitions. Because if it's equivalent, we can just merge them together pretty much and just keep one of them. It should be noted there's actually lots of algorithmic methods for minimizing automata, but we don't need to know any. So we haven't been taught one. The only one we've been taught is doing it by eye. So we had this question in some summative assignment. Just as an example. Here we can see we're starting at 1. B doesn't accept anything, but after we go to A, we can never get rejected. If we look here, once we're in 2, 4, if we go A, AB, AB, it doesn't matter what we do, we're always being accepted here. So it's not minimal. We can clearly see that because we can make a smaller one by simply having our 1 state with B not being accepted. After we do A, there's no way for us to be unaccepted, so we're always at 2. That's all I really needed to say about minimal automata. Following on, I don't know if anyone else has any further questions on it. Okay, and the next one is just regular expressions. The way I like to think about regular expressions, I just think of them as automata in my head. So let me bring up my notepad. The purpose, first of all, I always think it's more important to know the purpose rather than just knowing how to do it. Is automaton, although we can see like this, it makes sense to us. How it's going to be really hard to represent this in a program. Let's say you wanted to make something that would validate a postcode or not. You don't want to whip up a whole diagram and then I don't even know how you can represent this in a program and have all of the lines going in the correct place to all the correct states and then processing it. So regular expressions are a simpler way of representing this in our head. So for a regular expression, there's a few rules. You either write a character if you want just that character to be required to process it. So you can imagine here, just before A is our start state. And then we would need a transition to another one and that would consume the A. It's pretty much the same as automata, in that it's just going to process it one by one. The next rule is the star, which means this character or more than one. So we can imagine right now, 1, 2. This is just A by itself. Then this is going to be, this would be A star because it's 0 or more. So it could be 0. So we instantly are accepted. And then we can do it any amount of times, and we're still in the same state. Although up here, we're not accepted until we do just one of them. Yep. And then following on from that, similar, so that's A star, is A plus, which is a combination of both, which is just at least one A. So it's just this top one again. So we need at least that first A to exist. And then any amounts of A's isn't going to change it again. We just need at least that first one. So you might not be thinking of automaton in your head, but you could imagine if we had some strings, let's say A, we can read the top one as just 1A, accepted. So if we had AB, we had 1A accepted. We haven't processed for B yet, so we're going to have to reject it. The second one, we're going to see A star, so we just think any amount of A's, so this would be accepted. Of course, if there's anything at the end, or that's not A's, then it's going to be rejected. And finally, A plus, one or more, so it's going to accept everything similar to this one, just not nothing. That wouldn't be accepted. That's the only thing which A star would accept, that A plus 1. And of course, this would like reject both if there's like a B or something. Sorry. Finally, there's the A question mark, which, to be honest, the TAs rejected my answer for this, but then I had to get it changed, so I don't know if you should use this. This is equivalent to just A or epsilon, so it's an optional, 0 or 1. I think you might want to write this though, because I don't know if the TAs didn't know the question mark existed. I think we only looked at it once. Yeah. Then the final rule is we can bring in brackets, which work just as you would expect. If you had, let's say, a more complicated regex, A star, B star, A, this is going to mean any amount of A's, followed by any amount of B's, including 0 for both of these, then followed by 1A at the end. If we bring in brackets, this means this is going to be processed first, but we can process this any amount of times. So let me do this. So we can imagine just this right now is any amount of A's including 0, followed by any amount of B's including 0. So any amount of A's including 0, any amount of B's including 0, and then just an A. This is epsilon, is it? Because, yeah, I think that's epsilon. So any amount of A's, and then once we're done with that, we can move on to here. Any amount of B's, and then just an A. So if we introduce a star, we can do this bit any amount of times. So we could just loop back to the start. Sorry. Just for an epsilon transition, we can always go back to the start. So in the bracket, so precedence works just as in normal maths. So if we have something more complex, this inside bit we can do in any amount of time. So it's kind of nice to think about this as its own smaller processing bit, and then it's contained within a larger one. So AB by itself is just this bit, and then if we imagine this whole thing, we can now have an infinite or 0 amount of V's followed by our A. So I mean, I don't know how much Shay looked into. I looked a bit at Shay's. So if you want more in regular expressions, probably go look at his recap. I can't remember which one it was. I think you do quite a bit in your checking for DFA equivalents. As you go through, you've got you're doing your regular expressions as well on top. So I don't know if I've missed anything in regular expressions. Yeah, so I just did a few questions, if I remember where I put them. Just to check on the regular expressions. Oh yeah, sorry again. I just missed one thing. If you're in a bracket, or even if you're outside a bracket, the whole thing, you can just do an OR, which is going to work as you would which is going to work as you expect it would. So if we have AB here, we can just start at 1 and just go to either. We're just doing an OR, so A or B. 4, 5, So we can either, from where we start, we can either go to 2 or 3 and then continue processing there. And the same way we kind of encapsulate encapsulate the logic within our brackets, we can think about that first. So any amount of A's, any amount of B's, and then now we have this kind of smaller machine within our bigger one, which can be repeated infinitely. Yeah, so we've got just the letter 0 or more, 1 or more, 0, 1, and the or, and then our brackets on top of that. Okay. So I think I only wrote 4 questions here, 4 or 5 questions, just to finish with. So number 1, so we've got A bracket, B or C, close bracket, star. I want to know, does it match A, B, C, or D? Yeah. Does anyone want to try? We can go through it together. Okay, I'll go through them. So we can just read it through. We need at least 1 A. And then we have B or C any amount of times. Yeah. So if we start with it, let's check A. We've got A, at least 1 A. Then we've got B or C any amount of times. So we're going to do this smaller machine within the bigger one 0 or more times. So first of all, we process the A. And then now we're doing these individually. So we've got B or C. We know that's correct. So now we've done 0. Sorry, we've done the first one. Now we can go do it again. C, we accept. B, we accept. So in the end, this whole thing gets... just A. This gets accepted. Does that make sense? So we're doing this bit over and over again. So in the first one, this is B. And then in the second one, it's C. In the third one, it's B. Okay, B, A, B, C, B, B, C, D. So we accept, we're not accepting, but we're not rejected yet. We're in kind of a state right now. So A, we process the A, it's good. Now we could do, this whole machine is B, and then it's C. We're doing the machine again, sorry, this whole bracket bit. B, 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 C. We get to the end, there's D. We can't process that. We need to have something like this at the end, or something like that. But right now, this isn't accepted because there's D at the end, and we're not processing that. Okay, C. We need to start with this A. We kind of have a pointer right now. Let's imagine we have a pointer. It's pointing at the A right now. So before we do anything, we need to process this A, and the A doesn't exist, so we instantly reject it. Okay, D. So we start with A, and now let's process it. We got B or C. We got B. B or C again. We got C. We got A. But our pointer's now pointing at this whole bracket bit, which has been repeated, and we can't accept it because there's no A here. Does that make sense? So we accepted, I think, A and B. Oh no, just A. Yeah, we just accepted A. Alright. I've got 2 regular expressions here. Are they equivalent? Okay, so let's look. So what's the first one saying? we've got, at least for 1A, followed by B or C any amount of times. And the second one is saying we've got A, so we're starting with A again, followed by any amount of B's or any amount of C's. So they're slightly different in their meaning. In this first one, we could accept something like this, because we're processing it one at a time. So we start with A, and then we've got this whole thing, 0 or more times. So the first time it's B, which is correct. We can just do B. B again, C, B, B, C, B, C, 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 B. So any amount of times we can accept it, accept this like inner automata, a regular expression, so it's just B or C, any amount of times, so that's accepted. Over here, we're limited to only using B's or only using C's. So this wouldn't be accepted because we need our first A. And then here, we either have a choice of any amount of B's or any amount of C's. We don't have a combination of them. So here, it looks like we choose the B, any amount of B paths. So we go 0 or more B's, we do 2. And then we've reached the end. We've done this whole thing. We can't do the C because it's an OR, and we chose the B. So we get rejected at this point here. Okay. And then I've got this one just to do together. We're going to try and draw this regular expression into an automata. So we're starting with 0 or more A's, and then we've got 0 or more B's, 0 or more C's, but then this whole thing 0 or more times. Sorry, I meant to draw this as a... So let's try and draw this. So the first thing we start with is 0 or more A's. So like earlier, we're not changing, it's not required first of all. So after we start, we're going to end up in the same position even if we have no A's. And if we do have any A's, then we're just going to stay at the same state. And by drawing this transition, we're allowing the A's to happen. Because if that wasn't there, then it's a partial automata. And if there was an A, it would be rejected. Okay. The next point is we're going into this brackets bit. So let's just draw a transition. We'll just do an epsilon transition into here. So we got 0 more B's. So exactly the same. A B isn't going to change where we are. Followed by an epsilon transition into 0 or more C's. So right now what we've made is this. Apart from this needs to be accepting. So right now that's what we've made. And then we just need to make this last bit be able to loop itself. So after processing 0 more B's and 0 more C's, we have an option of restarting and going back to the start of here, which is the B bit. Oops. So we have the option of doing that. And also we had the option of doing 0, so this would have been accepting as well. And also because these are epsilon, it's all accepting anyway, so we also accept just nothing. Does that make sense? So we just kind of slowly made it. We started here, then we started with the end of it, and then we've just added the loop at the end and the initial accepting state. Okay. And that's all I had really to do. I mean, it's just the topics are quite small, and of course there's more in Shay's shows old lecture, which is in recap if you want to look more at regular expressions compared to automata and them at the same time. But yeah, that's all I wanted to do. I'm doing AI later, unsupervised learning, which is like 6 hours of content. So that should be fun. So, yeah, I mean, unless you have any more questions, that's it.